Today we're working on how to figure out what line will fit our data best. And the general idea is you want the points to not be too far away from the line. So if you had this line and these data points, how is it doing? We've got some that are farther away from the line, but we tried to draw it somewhat through the middle. But what we would talk about as far as the quality of that line is we want to minimize how far away those points are from the line. So we're going to be looking at those distances. I'm just going to kind of make up some numbers for how far away these points are. If they're below, I'll call them negative. If they're above, I'll call them positive. This one is right on the line, so it has a distance of 0. And let's just think about how we can tell if this is a good line or not. What if we just added up all those distances? We'd have these guys canceling each other out. We'd have these two canceling that one out. And overall, we'd have an overage of 1.5, which isn't too bad. But do we really want those points that are so far away from the line just to cancel each other out? So there's another way where you won't have all that canceling. It's called the least squares criterion. What we're going to do is square each of those distances. Once you square them, since they all come out positive, all of them still matter. This one matters a lot, and this one matters even more. And the one that was at a half actually doesn't matter quite as much, because when you square that, it becomes 1/4. So overall, we'd be looking for a line that takes all of those distances squared and makes that the least total possible. So the formulas we see today are all going to be based off of that premise, but we won't have to actually calculate those distances and square them. The equation of the line that we're going to find is in the y equals mx plus b form, and they call that the least squares regression line because of how it's calculated. You'll notice that the y in y equals mx plus b has a little hat on it, and we literally say that's y hat. And so that's sort of like the predicted value, or the line of best fit y value. I think this first point is really interesting. If you find the mean of all the x values and the y values, that ordered pair is on the least squares regression line. I just think that's cool. The slope can be found, thanks to somebody who did the calculus for us, using either of these slope formulas. Which one looks better to you? Well, this one requires you to find those standard deviations, and we know what a pain that can be. Whereas this one looks more complicated, but those are pretty easy things to figure out. But both formulas should work for finding the slope. Once you know the slope and a point on the line, which we should from the formula and from those mean values, we should be able to find the b in mx plus b, which is really just plugging in our xy point that we know, the slope that we found, and solving for b by subtracting that mx to the other side. So this looks like a special formula, but really it's just finding b the way that we used to in algebra class. Now we're going to do this example, and we've got, it looks like 6 temperatures at 6 different times over the day, and those are plotted on here, and it looks like those are somewhat linear. And we are going to find our least squares regression line. I'm going to trust that if you really wanted to, you could find the mean of all of those values, and you could add together all of those values. You could square them and add them together. You could multiply your x times your y and then add all of those together. But I will allow you to use your calculator if you would like to take that shortcut. Once you've calculated all of those values for the times and for the temperatures, and then time times temperature, we have this fancy formula for how to find the slope of the least squares regression line. So we've got our slope calculated as 11/7, and now we just have to figure out what our y equals mx plus b will be. Remember that I know an ordered pair that is definitely on the best fit line, and that would be the ordered pair of the mean x values, comma, the mean of the y values. And I also know the slope, so if I plug in all of those things, I can easily solve for b just by multiplying those together and subtracting them over. And so my line of best fit, my least squares regression line, will be written like this: y hat equals, and I think I like the fractional value for the slope the best, so 11/7 x plus, and then I just have to decide, I should probably stick with the one that's not rounded. And that's my line. I'm going to try to sketch it on this graph too. So I would need to find that y-intercept of 27.81. And I need to do a slope of up 11/7, or it might be easier just to find where this point is and just connect the dots. And I would say that that line fits the data pretty well. Now that we've done the calculations, I want to teach you 3 more vocab words. The first one is marginal change, and it's what the slope tells us about the variables. I've always wondered why slope is m, and maybe it's because of marginal change. We know that our slope is 11/7. But what does that actually tell us? And I think the best way is to think about how slope is rise over run. So if we think about how the rise is measured and how the run is measured, that'll help us get a label on that. So the rise is measured in degrees, and the run is measured in time, which I assume is hours. So I could say, since that's a positive slope, we have an increase of 11 degrees every 7 hours. Or you could say that it's an increase of 11/7 of a degree every 1 hour. An influential point is a lot like an outlier. With or without this point, the regression line would change substantially. And so I think you can see where, what if at 2 o'clock it were 50 degrees? That would be a major outlier, and that would definitely change the positioning of our best fit line. So I would say if we found out at 2 o'clock it was 50 degrees, that would definitely be an influential point. It would change our results substantially. Residual. This is something that my students have missed in the past, so pay attention. The difference between the regression predicted response and the actual data value. Remember that your y variable is the response variable, and x was the explanatory variable. And we're looking for the difference between the predicted from our y equals mx plus b, our y hat, and an actual y value. As an example, how about we pick the time 7 o'clock when it was 38 degrees. So we have an actual value at 7:38. And what we're going to figure out is what happens when we plug a 7 into our regression line. What kind of y hat does that give us? So you'll see that our line is predicting a temperature of 38.8 degrees when we know that the actual temperature was 38. So the residual is just the difference between that actual y value and our predicted y value. So in this case, the residual would be negative 0.8 degrees, which actually means that the predicted value is 8 degrees higher than the actual value. Next, we'll talk about interpolation versus extrapolation. Interpolation means inside. We're using the regression line to predict a value within the max or the min of the original data. So maybe I would use the line to predict what the temperature was at 10:30. If I plugged a 10.5 into that equation, that would be an interpolation for the temperature, because that point would be inside sort of the domain of the points that I already had. So then extrapolation, extra meaning outside, using the regression line to predict a value outside. So let's say I wanted to go back in time or forward in time and predict what was the temperature at 2 o'clock. If I took a 2 and plugged it into my regression equation, that'd be an extrapolation because it was outside of the data values that I used to make the line. In both of these cases, I was using that y-hat regression line to make a prediction for y values, right? What's interesting to know is that if you switched everything around, if we switched the temperature to the x-axis and the time to the y-axis, you would actually not come up with the same line in general. The slope wouldn't be 7/11ths like you might expect. And that's because those calculations that we used to make that line were assuming that the x was the explanatory variable. If you go back and look at that slope formula, it was heavily relying on the x value. Last thing for today is the coefficient of determination. We use the variable r squared for that, and yes, it is just the square of the correlation coefficient. This describes how much of the behavior or the variation of the y values can be explained by the x values. Here I've got a correlation between high school GPA and university GPA. And the correlation coefficient that was computed shows us that we have a moderately strong positive correlation. There's a lot of the values that are grouped pretty close to the line, but then we've got some scatter here and there. But what we want to talk about is the coefficient of determination. So we're actually going to take that number and square it, which comes out to about 0.61. So we are going to use that to talk about the explained variation and the unexplained variation. For explained variation, we are going to say that 61% of the behavior of the y variable can be explained by the x value. 61% of the variation in university GPAs can be explained by the variation in high school GPAs. On the flip side, we say that 39% of the variation in university GPAs cannot be explained by the variation in high school GPAs. That's the unexplained variation.